Well, good afternoon. This is Wednesday, the 23rd of January, 2019, 2:35 in the afternoon, about 5 minutes late getting started on differential equations class. I kept waiting for someone to show up. Justin, I saw him in the hall and said he wasn't going to be able to make it today, but so far nobody else is here either, so hopefully some will be coming in. So I'll go on and get started on where we left off last time. Can't think of any major announcements or anything to make. So let's get going. I was going to say on Friday I do have a meeting, but it's at 12:30, so it shouldn't be interfering with office hours, because my office hours are technically 8 to 12. So basically it just means I have 30 more minutes of office hours, or a portion of that, before the meeting starts. So anyway, nothing that needs to be said there. All right, so let's pick up and go from where we left off before. My mark is that we were on, we've been talking about explicit solutions to differential equations, and the definition on about midway through page 8 is Chapter 1, Introduction to Differential Equations, 1.1, Definitions and Terminology. This is the definition of an implicit solution of an ordinary differential equation. So this is definition 1.1.3. So here's what we got. A relation, let me get my pen set up. A relation, okay, now in pre-calculus algebra, remember, a relation we talked about was any comparison of any two numbers. Not necessarily a function, though it could be a function. Okay? So here they're using that term again. Let's see if that's the same thing. G of xy is equal to 0. Okay? It's said to be an implicit solution of an ordinary differential equation, ODE, ordinary differential equation, and the one that we're talking about is equation 4, which you find back on page, top of page, or near the top of page 5. Okay, that was your f of x, y, y prime, y double prime, all the way up to y, the nth prime of y, in other words, nth derivative of y, that's equal to 0. Okay, ordinary differential equation of that form on an interval I, some interval I, provided there exists at least one function so phi, got trouble reading that, phi that satisfies the relation as well that's that relation up there, g of xy is equal to 0, as the differential equation on I. Differential equation on that interval I. Now that almost sounds circular, okay? So let's see if we can plug it together. Relation, that relation, g of xy equals 0, is said to be an implicit solution of an ordinary differential equation 4 on that interval, in interval I, provided that there exists at least one function phi that satisfies the relation as well as the differential equation. There's at least one function that's satisfied. So indeed they are talking about this being a relation. It is an implicit solution provided there is at least one function phi that satisfies that relation as well, as a differential equation on I. Okay? Now, next statement, pretty true. It is beyond the scope of this course to investigate the conditions under which the relation g of xy equals 0 defines a differentiable function, phi. So we shall assume that if the formal implementation of a method of solution leads to a relation there, then there's at least one function that satisfies. Okay? If the implicit solution is fairly simple, we may be able to solve y in terms of x in one or more explicit solutions. A lot of blah, blah, blah. Let's do example 7 and see if we can make it make any more sense than what it sounds like it does now. Here's a relation. X squared plus y squared is equal to 25. And indeed, that's not a function. What is it? That's an equation for a circle of radius 5. Okay? Circle of radius 5. Okay? That's not a function. It's a relation. Because a circle of radius 5, obviously, anywhere from minus 5 to plus 5, it's going to intersect a vertical line in between x equal minus 5 and x equal plus 5 will always, every vertical line between those two will intersect the circle twice, one on top and one on bottom. Okay? So it is a circle. They also claim that it is an implicit solution of this differential equation. And here's the differential equation. dy dx is equal to minus x over y. Okay? On the open interval, minus 5 to 5. Exactly what I said where this is defined. On minus 5 to 5. Okay? Now, we're saying it's an implicit solution. And now they're going to turn around and say, by implicit differentiation, we show that it is a solution. Now, I don't think the two of those implicits have to be together, but they quite often are. So let's take a derivative of this. Derivative of this will be 2x plus 2y, y prime, because y is the derivative of x. That's equal to 0. So let's solve that for y prime. And we find that subtract 2x from both sides, and you get 2y y prime is equal to minus 2x. Divide both sides by 2y. Those both go out, the 2's go out, and you have y prime, which is dy dx, is equal to minus x over y. Sure, it is a solution. That relation is a solution to that differential equation. Okay? If you were to turn around and solve this for y, you'd have that y squared is equal to 25 minus x squared, and then y is equal to plus or minus the square root of 25 minus x squared. Okay? Pretty clear. Those are two functions. Okay? One with the positive and one with the negative. Two different functions that both satisfy the relation, okay, and they both solve this differential equation. So that is an implicit solution. They draw this over here. Again, a circle of radius 5, and then you could either do the top half of the circle or the bottom half of the circle separately, and those are two functions that solve the differential equation. Now, that said, let's move on to the next topic, and that's families of solution. They're going to introduce something that's fairly important here, and may not seem that way to begin with, but we're going to use it over and over and over again. Study of differential equations similar to that of integral calculus. When evaluating the antiderivatives or indefinite integral in calculus, we use a single constant c of integration. Analogously, we shall see in Chapter 2 that when solving first-order differential equations, that would be something of the form. Let me clear my screen here so we can do this. F of x, y, and y prime equals 0. This is in that same form as equation 4 before. That's the first-order differential equation because the maximum derivative is the first derivative. Okay? We usually obtain a solution containing a single constant or parameter c. So first order here results in a single c. Okay? Single constant or parameter. Solution containing that constant c could be expressed as g of x, y, and that constant c, okay, equals 0. That would be your solution family. That's called a one-parameter family of solutions. Your parameter is c, and your variables are x and y. Okay. When solving an nth-order differential equation, that would be the f of x, y, y prime, y double prime, y triple prime, dot, 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 all the way up to the nth derivative of y. That equals 0. That's basically your equation 4 that we had before. We seek an n parameter. Here you had one derivative, one parameter. Here we have up to the nth derivative, so you're going to have n parameters. So your G, general solution, or the relation that is your solution, will be x, y, and then C1, C2, C3, dot, 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 all the way up to C sub n. Okay, equals 0. Okay, that means that a single differential equation can possess an infinite number of solutions corresponding to an unlimited number of choices for your parameter, just like we've done in others. And by the way, it is getting cold in here. I wonder if the temperature is dropping outside, because it was fairly pleasant last class. Of course, I had a few more people in here, but it is really cold now. I'm going to pause for just a minute because I've got to go see Dr. Bryant before he... Okay. For some reason, it's advanced a page there. Sorry, I had to talk with Dr. Bryant about something. He just came in, so he'll still be teaching when I have to leave to go to the other campus, so I needed to catch him then. All right, so anyway, for the order of your differential equation determines how many parameters you'll need. Okay. We already said that. A solution of a differential equation that is free of parameters is called a particular solution, and we'll talk about those later, and I'll tell you right now the symbol for that. If y is a solution and it happens to be a particular solution, it'll be y sub p. Your general solution will always have parameters in them. The y sub p will not have a parameter. Okay? A solution of a differential equation that is free of parameters is called a particular solution. The parameters of a family of solutions, such as this one here, that's a family of solutions, in degree, so it's n parameter family of solutions, are arbitrary up to a point, okay? For instance, in the preceding example 7, I think it is, they're talking about, yeah. I already have erased that screen so you can't see it. Let's go back to x squared plus y squared is equal to c. Before that was 25, and that was circles of radius 5, okay? But now, writing it this way, it formally satisfies equation 8, which was the differential equation, dy dx is equal to minus x over y, okay? Because we did, when you took the derivative, remember when we had a c, or a 25 there, when you took derivatives, 25 disappeared. Derivative of 25 is 0. So your solution didn't depend on what size circle it was. It just said it was circles of any radius c. Well, up to a point, they had to be positive. You couldn't have a c who was negative, okay? And nor could you have a c that was 0, unless, of course, you talk about the trivial solution. So that's sort of getting at what they're talking about here. The c's are arbitrary up to a point. This one couldn't be negative, for instance, okay? All right. That's to get real solutions anyway. So let's look at example 8. And I'm going to apologize because I feel like I've got to sneeze. Like I said, this room has gotten really cold, and I wonder if the temperature is dropping outside. And my head's clogging up, so if I'm getting harder to understand, that's the reason. So let's go to example 8, which is the bottom of page 9, if I can get my cursor to operate. All right, the A part. For all real values of C, the one-parameter family, y is equal to cx minus x cosine x, is an explicit solution, of the linear first order equation xy prime minus y is equal to x squared sine x. Oh, here he is. All right, coming at a good time. Let me move students in here. I don't turn on the projector. Obviously, I don't need it. And I don't have the lights proper for the projection because I saw one student when I was coming up in class. He said he couldn't be here today. I didn't know that was going to be the whole class up until now. So, and this room has gotten colder since my last class. When it rains, it pours, literally. Okay, so we have 2 students here. Dan is here. So I don't have this mark.
Wow, it feels much colder in this room than the rest of the school.
What's that again?
It feels much colder in this room than in the rest of the school.
I know. And earlier today, it felt about normal. So evidently the system is shut down, or else it's just gotten really cold outside, and we're leaking in pretty badly. And with no hot bodies in here to...
I think the windows are bleeding the hot air out pretty fast.
yeah.
It also smells a little damp.
Yeah. Okay. So, 238. This is the 23rd. Dan's here. Paige is here. All right, 2 in a row on alphabet too. All right. Now, I was just about to do, if you got your text, It's in Chapter 1, which is Introduction to Differential Equations, 1.1, Definitions and Terminology, and we're dealing with families of solutions, and this is example 8, the bottom of page 9. And we're just told that it says for all real values of C, here's a one-parameter family, y is equal to cx minus x cosine x, and they say that's an explicit solution for the linear first-order equation, this one I've just written here, xy prime minus y plus x squared is equal to x squared sine x. On the interval, this is where I left off, on the interval minus infinity to infinity. Okay. Now they say verify, and that's not a bad thing to do because that's a lot of what this first chapter is going to be doing is verifying that a given solution is a solution to a given differential equation. Okay? So how would you go about verifying that? What would we need to do?
We need to basically find the matter of asymptotes.
Don't need to worry about that right now. It says it's good everywhere, so I would.
Some kind of standard form to where we can actually like plug in current, where we can integrate it. No.
Again?
Would we be trying to get it to where we can integrate it?
Okay. Well, if you were trying to solve this one, not knowing the answer, that would be an option.
Okay.
Well, what they've done is said that's the solution. Verify it as a solution to this.
Okay.
Verify what they're saying is true. So what we do is take their suggestion and we're going to plug it in here. But what do we need to know before we can plug it in? Y prime. So the first thing we're going to do is take a derivative.
Right.
The Jesus answer, right? I told you all that one, didn't I?
What?
No, never mind. Okay.
You did.
Yeah, okay.
For differential equation, Jesus answer is derived.
Yeah, okay. So let's first take derivative. What is your y prime? If that's your y, what's your y prime?
Is that C to that?
C, yeah. So what's the derivative of cx? Second? Okay. If y is equal to cx, we're just going to do that part now. What's the derivative of y? It'll just be c.
Right, because the derivative of x is 1.
Right. Okay. Minus, now here comes
Oh, yay.
a product rule. Second?
Cosine gets to get in the way here. Derivative of cosine x is minus sine x.
Okay. So then this would be a plus. It's the first times derivative of the second. And the first is x times minus cosine. So that's what makes it a plus. Minus sine x.
Yeah.
Minus, left over from before. Normally it would be a plus, but it was a minus carrying across here.
Okay. Yeah, you're right, because it's the minus y.
That's the first part of the product rule. First time derivative of the second. The second part is
Oh, been too long.
first time derivative of the second plus the second time derivative of the first. The second is cosine x. Derivative of x is 1. Right?
Yes.
Okay. So there we've got our y prime. Okay? So let's see if x times y prime, that would be xc plus x squared sine x, right? X times that second term, minus x times cosine x. There's xy prime, right? Minus y. Well, there's your y, so that's going to be a minus cx, minus a minus, which will be a plus x cosine x. Okay? The question is that equal to x squared sine x? Well, let's see. Here's a CX. There's a minus CX. Those add to 0. Here's a minus X cosine X, a plus X cosine X. Those add to 0. And sure enough, those two things are equal to each other. So yes, indeedy, that single parameter system with one parameter C in it is a solution for this differential equation. And this differential equation is a first order differential equation because the maximum derivative is first derivative. It's also a linear first order differential equation because this is the only y thing that shows up here, only y thing that shows up there, and this is all on the other side, it's all a function of x. It doesn't matter whether that's linear or not. So it's a linear first order ordinary differential equation. It's one that has a single parameter solution. And that is a solution. Now that doesn't say it's the only one, but this is one. Okay? And that C could be anything. Completely arbitrary what value of C you put in there. An example I was giving before y'all came in was of a, let's see, I'll make sure I turn the projector back on, the recorder back on because I stopped it to talk to Dr. Bryant for a minute, but I did get it back on. I don't recall, and it wouldn't really fit here either anyway. But if for some reason C could be negative or C, something like that. Yeah, I remember what it was. A solution that was x squared plus y squared is equal to C. Single parameter system, right? But guess what? That C can't ever be negative. Because if you're squaring x and adding it to the square of y, it can't be negative. So a lot of times they're not completely arbitrary. This one is. It could be anything.
Wouldn't that give the problem imaginary solutions?
Yeah, you could have complex solutions with imaginary parts to them, but most of the time we deal with the real number system. Yeah, so if that was a requirement. So that was the A part of example 8, okay? And what we did, we verified it. Now, all we've done is gotten that far. Then it says, and y'all both got books, so I'm not going to hold it up in the light here. Figure 1.1.3 is a graph of some of those solutions. C equals 0, C equal positive C's, or a couple of negative C's. Okay. What's that?
It's really hard to see why the definition of this is a linear first order equation given how non-linear graph is. The
graph looks, yes, but it's the differential equation that's linear, not the solution that's linear. Okay. So that shows some of the particular solutions for that family for various choices of C. For instance, one of these, if C were 0, then it would be y is equal to minus x cosine x, and that's the blue one in that graph that they show here. Okay? So let's look at B. That was the A one. Here's a two-parameter family. Now, just because it might take a little more room, I'm going to erase this one. Is that okay? These don't depend on each other. So, okay to erase at this point? Okay. So here's a two-parameter family. Y is equal to C1 e to the x plus C2 x e to the x. Okay? Now, it claims that this is an explicit solution to the linear second order differential equation. Two parameters, it must be second order. And here's the differential equation. Y double prime minus 2 y, I've lost it, 2y prime, there it is, okay, plus y is equal to, I said plus y and wrote plus 1, plus y is equal to 0. Okay? Now, it says verify that that is a solution. Since we had so much fun doing it a little while ago, let's do it again. What are we going to have to do to verify? Second? Okay, do what again?
I'm sorry, differentiate.
Yeah, take a derivative of y and gives you y prime is equal to what? C1 e to the x is the first part, absolutely. Plus
Are we going to use product rule?
yep, you'll use product rule again. Now the C2 is a constant. It can just come out front and just do the product rule on the x e to the x. And what does that give you?
X e to the x.
X e to the x is the first part of the product rule. Then you use the C2 again for the second part. And what will that be?
Sorry. What was your question again?
What's the second part of the product rule? Product rule says C2 times the first times the root of the second, that's what you did, plus the
Derivative of the first.
derivative of the first,
Which is e to the x.
just e to the x. Yeah, the derivative of x is 1, and then times e to the x. So that's plus C2 e to the x. So there's your first derivative of that solution. But we also need what?
Y double.
Yes, we need the second derivative. Y double prime is equal to, let's take the derivative of y prime, and what do you get?
I'm getting lost.
Huh?
I'm getting confused here.
Okay, just take the derivative of that line you just did. C1 e to the x,
Yeah, C1
again.
to the x.
So what's the derivative of that?
E to the x.
C1 e to the x, okay? Plus, and that's the same as we had before, so that's going to produce the same result, which is going to be a C2x e to the x plus C2 e to the x, right? Because this term is just like that term, so its derivative is going to be just like that derivative was. But then you got this one again, and what does that give you? What's its derivative? That's the only one we haven't done yet. C to the, okay, and there we had one, so this gives us two of those. 2C2 e to the x. All right. Now let's plug and chug. Y double prime is C1 e to the x plus C2x e to the x plus 2 C2 e to the x. My writing stinks, but I hope you'll get by with it. Minus 2 times, where is my, there it is, okay. I'm going to plug in what y prime is, C1 e to the x plus C2x e to the x, okay, plus C2 e to the x, okay, plus your y, which is C1 e to the x plus C2 x e to the x. And supposedly this is equal to 0. Okay? That's what that claims. Let's see if it is. Well, here we have a C1 e to the x and another C1 e to the x. But here we have minus 2 C1 e to the x. So those four add to 0. The three terms add to 0. So that one with the minus 2 in there, and that one. Those add to 0. Okay, I'm going to leave the minus 2 because we've got to multiply it through the others too. I'm skipping a couple steps here just to save some time. So here's a C2e to the x. There's a C2x e to the x. And here's 2 C2 minus 2 C2x e to the x's. And those add to 0. Right? All right. And then finally we have a plus 2 C2e to the x. And here we have a minus C2e to the x. So sure enough, those add to zeros as well. Okay? So, yep, that does work. Okay? So we know that that 2-parameter system is a solution, maybe not the only solution, but is a solution to that differential equation. All right. We've just verified it. And then it says figure 1.1.4, which you see there. We have shown 7 of the double infinity solutions to in the family. And why do they call them double infinities? Okay.
Negative and a positive.
I guess that may be it. The solution curves in red, green, and blue are graphs of the particular solution y is equal to 5x e to the x. Where C1 is 0 and C2 is 5. And y equal 3e to the x is C1 is 3, C2 is 0. Oh, they're just naming 3 of them.
Where are they getting those numbers?
They just pick them, you know, okay, again, the C's are completely arbitrary. So they just picked a variety of them. And I'm trying to, the red, green, and blue. So the red is the one going up pretty sharp. That's 5x e to the x. That's where C1 is 0 and C2 is 5. The y is equal to 3e to the x would be the green one, which goes up more slowly than the red does, but doesn't dip as low. And that's when C1 is 3 and C2 is 0. And then the blue one is when C1 is 5 and C2 is 2, and that's peaking and then going downhill really fast. So anyway, just 3 of the solutions. The other, what is it, 3 black ones they show, you can pick out approximate values that would have given those. Okay. Now, sometimes differential equation possesses a solution that is not a member of a family of solutions of the equation. That is a solution that cannot be obtained by specializing any of the parameters in the system's family of solutions. Such an extra solution is called a singular solution. Okay? Now, a little bit earlier, you go back 1 page to the middle of page 9, says a solution of a differential equation that is free of parameters is called a particular solution, that you don't have any parameters in it. This now, though, is talking about something different, a solution that cannot be obtained by specializing any of the parameters in the family. That is called a singular solution. Now, the difference is a particular solution is once you have chosen a certain number of parameters, so you put those in and they don't show up anymore, that's a particular solution. Like those 3 we were just talking about, the red, green, and blue, you just pick different values and they make particular solutions. Not the general solution, which has the C1 and C2 in it. The singular solutions are ones that don't depend at all, cannot be obtained by specializing any of the parameters of the system. Okay. Now they give this example that we kind of talked about before in a different context. Okay. Here's a solution. I think I can get it all here. Y is equal to 1/16 x to the 4th. Okay? Excuse me. And y is equal to 0. These are two solutions to the differential equation. Excuse me, I got the hiccups. dy dx is equal to xy to the 1/2. Okay. Now, I think we may have done this before, but if we haven't, you can still do it here. If that's your y, then certainly your y prime dy dx is going to be 1/4 x cubed, right? Okay. So if you put 1/4 x cubed, that's your dy dx, and they claim that's the same as x times the square root of y. Well, the square root of y is 1/4 x squared, right? When you take the square root, this is y, the square root of y. By the way, this is not a linear solution, linear equation. That is not to the first power. This is to the first power, but that is not. So this is not a linear solution. It's okay, it's a solution, but it's a non-linear solution. But if you do y to the 1/2, that's the square root of y, that would be 1/4 x squared, right? Take the square root of 1/16, and you get 1/4. The square root of x to the 4th would be x squared. So this thing would be that's clogging up. This thing would be 1/4 x squared, multiply x by it, you get 1/4 x cubed, and that's exactly what you get when you take the derivative of this, 1/4 x cubed, right? So yeah, this is a solution to that, okay? Now, that's also a solution to this, right? When y is equal to 0, derivative of y is equal to 0, square root of y is equal to 0. It doesn't matter what x is, x times 0 is 0. Well, that's a singular solution, okay? It's also called a trivial solution. But it's a singular solution. It has nothing to do with parameters anywhere, okay? It just is an extra solution there, okay? And by the way, those are solutions for any value of x, I'm pretty sure. Yeah, x equal negative infinity to infinity. Yeah. I do have a problem with that because if the x were negative, the y up there is always positive because you're presence of the 4th power. And that y always positive, you can take the square root of it, and that would give you 1/4 x squared. But there's nothing down here that says that this x has to be positive. But if it were negative, that would then I guess it would still be okay because it's just a derivative that would be negative. It's not the function itself. That can't be. So yeah, I guess it's still okay. I would have guessed otherwise, but it seems like it's okay. Okay. Now they say in section 2.2, which we haven't gotten to yet, so let's just wait until we get there. Let's move on to example 9. Okay? I thought that was going somewhere we could do pretty quickly, but it isn't. Okay. Now, the title of this is using different symbols, which frankly seems like it's not a big deal. here are some functions. X equals C1 cosine 4t. Okay? Here's another one, X equals C2 sine 4t. Okay. Goodness gracious, I'm getting dizzy. Head's all clogged up. Okay. Where C1 and C2 are arbitrary constants or parameters, both solutions of the linear differential equation x double prime plus 16x equals 0. Okay. Now I bet you they want us to verify that as well. For some reason my pen's not writing consistently. Okay. So let's see what we get when we take, now, they're doing something a little bit different in this problem. Number one, they're using x as the dependent variable, where we usually were using it as independent. But before, you'd have a single solution, okay? Even when you had two parameters. You just combine them together, like 8b, you put them together, which you can always do. C1, whatever function you had, well, C1 times whatever function it was, plus C2 times whatever function, just like they did in the B part, with one dependent variable, y, okay? In this one, they're giving you two functions, x and x, but they're different functions because one has one parameter, C1, with cosines, the other has another parameter, C2, with sines. Okay, so those are arbitrary constants, but they say both are both solutions to the differential equation. So now we've got two first derivatives and two second derivatives to take. So what's your x prime?
Negative C1 sine.
Negative C1 sine of 4t, but, goodness gracious, I'm trying to write this, and it's just getting worse and worse the more I try to correct it. Okay. You left out one little thing. Chain rule would put a 4 there. From there.
Yeah, that chain rule always tells me.
What's that?
The chain rule
Oh,
always tells me.
yeah. All right.
Sorry.
Yeah. You take derivative of the outer of the bigger function, but then take derivative of the inner function times that. So that's where the 4 comes from. Okay? And if you do this one, x prime, that's equal to?
Negative 4.
No, not negative here. Derivative of sine is positive.
We're doing
Yeah, we're doing the other x. Yeah, sorry about that.
4C2 cosine 4t.
4c2 cosine 4t. Okay? Now let's do our x double prime. That's what I think you were starting to do. What would that be? I think he started it before.
Negative 16
16 C1 cosine 4t. And the other one is a x double prime equal
16 C2
negative 16 C2 sine 4t. All right. Now, let's do each of these separately to see they're both solutions. This x double prime is this one plus 16 times this, well, sure enough, this was minus 16c1 cosine 4t plus 16c1 cosine 4t. Certainly that's 0. Okay? Over here on this one, this x double prime is minus 16c2 sine 4t plus 16 times c2 sine 4t. That's equal to 0. So sure, both of these satisfy that differential equation. Now, don't know if they're going to introduce this to you. I think they are. Yeah. Finally, and here's I think what they're getting at here. It is straightforward to verify that a linear combination of the solutions or the two-parameter system is also a solution. So basically, if this is one solution, I'm real tempted to call that x of 1 and x of 2, okay? Then you can say that C1 x of 1 plus C2 x of 2 is also a solution, okay? Where these see. And in that sense, these becomes the parameters down here, the linearization parameters. So you could have put them up there separately, or said cosines 1, sines 1, so any linear combination of those is 1. Because when you do all this stuff and add them all together, just like they did here, they all add to 0. So that's all it's saying. It's sort of a weird way to go about doing it. It is straightforward to verify that the linear combination of the solutions or the two-parameter set, and here's how you would write that, just like I wrote it here. Well, I'm going to write it here. X is equal to C1 cosine 4t plus C2 sine 4t. Okay, that will also be a solution. So you don't have to do two separate ones, just combine them together with different parameters, and you've got your general solution. Now, the next one is a rather, on the surface being a little strange, but it's not necessarily. Let me start with a clean page here. Sometimes these get on a tad bit tedious, and you're trying to figure out, well, what are they trying to show here anyway? And sometimes it's not all that obvious, but it could be. One parameter family of quartic meaning to the fourth power. Monomial functions, here's one, y is equal to c x to the fourth, okay, is an explicit solution of the linear first order equation xy prime minus 4y is equal to 0. Now, just as a quick review here, linear, because this and this are only two first powers, the derivative and the y, only to first power. Ordinary, of course, these are derivatives, not partials. First order differential equation. Okay. So we've got what kind that is. Not that it really matters, but that's what kind it is. Okay. Now, we say that's a solution to it. real easy to get what do you do first? Derivative, y prime is equal to
4 CX3 cubed.
cx cubed, right, okay. Now if you take this and plug it in, x times y prime, that would be 4c x to the fourth minus 4y, which is c x to the fourth. Sure enough, that's equal 0. Pretty obvious that is. Okay? And that is a solution on the interval minus infinity to infinity. Those are all the values for x's, because x can be positive or negative. Your c's, depending on whether they're positive or negative, could be going up or down because the x to the fourth is always positive. Okay. All right. The figure that you see there, one of those, the red one is on, no, the blue one's on top. That's with C positive. That's always going to be positive. Y is equal to CX to the fourth, always curving up. If C is negative, however, the one that curves down, the red one, is curving down. So, and you could put any value for C and stretch them and squish them further or whatever, positive or negative, they'd work. Okay. Your parameters would then be the ones they drew here was in the text. The blue is C1 and the red is C1. The blue is C equal 1, the red is C equal negative 1. All right. Now, what if they did something kind of wacko like this? They say your solution, y, is a piecewise defined solution. And it's going to be minus x to the fourth any times x is less than 0. And it's going to be x to the fourth. I don't like this. I'm going to leave it blank now for a reason. Well, greater than 0, okay. What I wanted to do, that leaves off 0 altogether. Now, it really doesn't matter which one you put. To have it continuous everywhere, you really do need to include the 0 in there. Otherwise, it's just not even defined there. So you could put the minus sign here or here. It doesn't matter because of x equals 0. They're the same values. So it doesn't matter whether you put the equal sign here or here, but you really needed one or the other. Okay. That was the only little thing I had for that. Now, this is also a solution to this differential equation. You can plug it in and see. I mean, it maps the same space as the two that are horseshoes on top, of each other. It's just one only does one end and one does the other end. Okay? The point here being, even though that is also a solution, albeit a piecewise defined solution, it doesn't come from either one of those. Because it has one C1 for half of it and the other C1 C for the other half, and your solution is only one C. Okay, so they're saying that you can't have other solutions that don't fit into that particular differential equation. Okay, you can have yet another one that you don't get from a single choice of C. If you did two choices of C, yeah, it works fine. But then one choice would be for negative x's and one for positive x's. All right. Now, I really don't think there's a lot to be said for this. I'm just going to read it. Systems of differential equations. We must deal with systems of differential equations. A system is two or more equations involving the derivatives of two or more unknown functions of the dependent variable. So I'm not going to go into any more than that. A solution for such a system as this dx dt is equal to f of t, x, and y, and dy dt is equal to some different function g of t, x, and y. Now, that's a system of two differential equations, because those are two different functions there. Okay. Now,
You're saying they're two different functions because of f and g?
yeah, because f and g. They have the same variables, but they're two different functions. Now, the first one, the dependent function is the x, independent variable is t. Second one, the dependent variable is y, but the independent variable is still t. So, if they may be functions of t, of course, because that's the independent variable, and both the x's and y's, the x and y's are not independent variables, they are the dependent variables. Now, why x shows up in this y, this derivative here, is not entirely clear, nor does why y shows up in this one. You know the t's got to be there. I mean, that's the independent variable. But that the x and the y show up in each other's derivative is a little bizarre. It makes you think they may be dependent, not independent, but they claim here they are independent solutions. So we're not going to do any more than this. All they say here, a solution of a system such as this is a pair of differential functions, x equal phi1 of t and another phi2 of t, defined on a common interval I, and that's all they say about it. So we're not going to do any more than that. Now, these remarks at the end of each section sometimes are very helpful and sometimes just muddy the waters unbelievably. So most of the time I'm not going to do anything with that unless I see something in it that I know we're going to need. And this one, I just don't. We are going to do something like that first equation 11 occasionally, but not as a general practice. And the second one, example 12, even though we may have some minimal use for it, I don't think I'll go into that right now.
That's almost confusing. You're taking the differential of the integral.
I'm sorry?
That's almost confusing. You're taking the differential of the integral.
Okay, where do you see that?
For number 12.
Number 12.
The D,
Well, yeah.
dx.
Yeah. Actually, that's almost like your fundamental theorem of calculus, that a derivative undoes an integral, and an integral undoes a derivative. The thing that I found a little surprising is they don't relate the answer back to either F or F prime, but they just don't. But again, that's going a little bit deeper than what we need to go. So, oh, there's another page of this. Now, that last definition there, the bold type general solution, if every solution of nth order ordinary differential equation on an interval I can be obtained from an n parameter system, blah, 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 then we say that family is the general solution of the differential equation. We're going to come up and use those terms again. So stand by for that. Homework exercises here, because the answers to the selected odd number problems are in the back of the book in section on page ANS1, answer 1. You have to go back there and find it because it's not particularly easy to find, but it's in the back. So do any of the odds 1 through 7, and they show a couple of different notations there. The dot notation I haven't seen used at all frequently, but they use it. Do number 9. Do number 9. Okay. Do either 11 or 13. All these should be in the answer portion. Do either 15 or 17. Do 19. Either 21 or 23. Either 25 or 27. Now those are getting into those with the derivatives of, no, actually not. Try to do those if you want to. If it gets too bogged down, you can forget about that one. Try to do 29, either 31 or 33 or both. 35, do. Either 37 or 39, you should be able to do. 41 is getting a little more difficult. Give it a shot if you can. Now, what my observations are is the odd numbers on the discussion problems typically aren't in the back. Some of them are, but typically they're not. So you don't have to do any of those unless you want to. However, I wouldn't suggest just ignoring them. At least look at those things. And here you see a figure that they are describing as the folia of Descartes. So there's some potential paper topics. Number one, who in the world is Descartes anyway? Pretty famous character. And number two, how did he develop the folia of Descartes? Number three, what is the folia of Descartes? How is it used? Is there any actual thing in science or engineering that actually uses that? So if you can find a paper topic in any of these, that's not a bad thing to find. Other than that, you don't have to mess with those. So let's move to 1.2, which is initial value problems. Are we out of time?
Yeah.
We are. So I need to stop. So we'll pick up with 1.2 next time. So I'll just put the marker in here, and we'll start right there. Okay. So let me end this.